Hello and welcome. I hope you enjoyed your water quality testing. I know it wasn't as ideal as if we were in the classroom and testing the water ourselves. I apologize for that, but that was the best we could do, and I thought Claire did an awesome job of walking you through each of those water quality indicators and kind of telling you more about them, as well as testing her own backyard river right there in the Chesapeake Bay. So today we're going to go and talk just a little bit about water pollutants and think about maybe why our water is showing those testing, why our water might show different testing levels. So you're going to go to these notes, and I apologize, none of you actually have these printed out. So you're going to want to go to the editable water notes, type, make sure you file, make your own copy, and then you're going to type in these little text boxes right here. But until then, sorry about flashing the answers to you. Our bell ringers this morning, what or how do scientists determine the health of a body of water? We learned about that yesterday. It is by testing these different things that we call water quality indicators. They show us if the water is healthy, not healthy, average, and so forth. What might be a cause of a river to have a low DO reading? We also talked about this yesterday, and for other reasons. So one thing that you learned with Claire, it simply might be that there's not a lot of movement with the river. Stagnant water typically has pretty low DO readings, so things like waterfalls and rapids will really help increase that DO level, just because more water has the opportunity to mix with the oxygen, dissolving it. Decomposition of species. So if we have a lot of death, like when we talk about eutrophication, the Thursday of last week, so quite a while ago, but decomposition of different organisms can also cause a low DO level because those bacteria come in and break down the different organisms, taking up the oxygen of that system. Also, we learned that as temperature increases, our ability to dissolve gases decreases. So an increase in temperature can also cause, or like a hot water, having hotter than normal water can also cause a low DO reading. Okay, so here's where your notes start. We're going to talk about point source pollutants versus non-point source pollutants. A point source pollutant is located at a specific place. It's easy to identify and monitor and regulate because we know where it's coming from. We can point to exactly where it comes from. Our example here is like a sewage pipe. If we find sewage in our water and we trace it back to that sewage pipe, it's likely that the sewage is coming from the sewage pipe. Do you see how we could point to exactly what's polluting our water? Other examples are like really specific chemicals that not everybody uses, like a couple years ago, we talked about this a little bit, but a couple years ago, a chemical company near Fayetteville started releasing Gen X into the water, which was a carcinogen, meaning that it causes cancer. And people in Wilmington were getting really, really sick because it was polluting their water supply. That would be an example of a point source pollutant. We know exactly who polluted, and they're easy to identify because we can walk up to them and say, hey, we know you're polluting. Here's how you're doing it. We're going to monitor it, and you need to decrease it. You need to find other ways to operate it so you're not polluting as bad. On the other hand, or on our other end of the spectrum, we have what we call non-point sources, and these are water pollutants that are typically found over broad areas. Again, they're difficult to identify and control because we don't know where they're coming from. We can't exactly say you're doing this, so you need to stop. So it's difficult to control. And often, because non-point source pollutants they're much broader, they're spread over a wider area, they're expensive to clean up. One example of this, and a really good example, is runoff. So runoff, like we'll talk about in a second, water carries everything. So as the water is running off, it's carrying the pollutants of whatever it passes over. Non-point source pollutants, again, they're difficult to identify and control. They're difficult to mitigate the effects. And unfortunately, a lot of our water pollutants do fall into that non-point source category. And there's just, besides being more mindful citizens and more mindful business owners, there's not much we can do about them. So it's your job for your generation to start thinking about how do we manage business and agriculture and whatever it is with the earth in mind and the environment in mind so that we aren't polluting the earth. Okay? Some possible sources of pollution, be that non-point or point source pollutants, our agricultural activities. So sediment also can be and is often a non-point source pollutant. You might not think of it, but again, we talked about when the sediment mixes with that water, it can prevent photosynthesis, and it can also be hard for the organisms in the water to see, or even harmful to those organisms. So the sediments eroding into the water is an issue. It increases our turbidity. Again, it can decrease photosynthesis, and as we learn in ecology, the plants, the green stuff's the base of our food web. So if we don't have those, then we're not having a food web, and all the other species are going to be affected negatively as well. Fertilizers and pesticides, again, recall one of water's properties is that it's a universal solvent. So it's picking up everything that it passes over as it runs off, including those fertilizers and pesticides that we put on our fields for our crops to grow. We want our crops to grow, but we also don't want to be polluting the water, because those fertilizers can cause eutrophication. Remember, the algae blooms and then the algae dies, and then bacteria come and they use up all the oxygen and everything dies because there's no oxygen. So that can happen if we have too many fertilizers. We can kill unintended organisms with those pesticides, and we can even get so many plants or green stuff in our system that it blocks out the sunlight, or it can block the flowage of a stream. And then bacteria from livestock as well. So remember, as the water is running off of that field that the cows lived in and love to be in and do their business in, that's flowing into our water systems as well. So agriculture actually stands as the #1 cause of water pollution. Industries and factories, so those can also cause a source of water pollution. Even thermal pollution, so we're going to talk a lot about this in earth and environmental science, but thermal pollution is a big deal. Remember, we talked about the fish, some can only survive in a certain temperature of water. Even if my factory is just putting hot water back into the stream, if the water is too hot and it raises the temperature too much, it can cause death in the system for those very specific temperature organisms. Mining, the coal dust can also get into our water systems and cause negative effects, whether that be like the sediments blocking out sunlight. It could be kind of choking the organisms. You know, if you can imagine, the dust and sediments could get inside the fish's gills. They can't move. Again, anything that is suspended in the water column is going to block out sunlight, so that's bad. Parking lots, whether you think about it or not, maybe you will think about it the next time you go see a parking lot, but parking lots can be a huge source of water pollutants as well. Any oil, gas, whatever your car is leaking, or heaven forbid, though I hope and know that none of you are polluters, but anything that you throw in a parking lot because you don't want to take it to the trash can, that's eventually going to get picked up by the water and moved to either the drainage, which ends in which it's either going to end in go to a drainage for the parking lot, like, you know, the underground sewer thing, which will eventually lead into the river or the ocean, or it's going to go into a river just all on its own. So parking lots are a big source of issues. Even if you think about car washes, all that soap and suds and whatever else they're putting on your car, wax, that can also be picked up from the parking lot and pulled into the water system. Human-made materials like plastic, again, littering, throwing things into the river, big things, that's an issue. And then, again, sediments. So sediments are an issue, whether that be through agriculture, like the fields have eroded, or even new construction can also cause an increase in pollutants. Testing for pollution, we're going to go over these real quick because we talked about this in a lecture and we did our activity on it yesterday. So we can check the bacteria levels. High levels of bacteria typically mean that we have contaminated water. Levels of DO, if I have low levels of DO, that means there's low life. Things need oxygen to survive. If there's not enough oxygen, there's not many organisms. And usually when there's not many organisms, that tells me that the body of water is dying. We call that hypotonic, I believe. A chemical analysis, so we're going to check our chemical levels, like our nitrates and our phosphates. Remember we talked about those. We're going to see if eutrophication is happening. eutrophic conditions, again, too much nitrogen or phosphorus inside the water. It's eroded from our agriculture fields and fertilizers, and then that causes the algae blooms. Algae bloom, live a big happy life, get really, really big, block the sunlight, but then eventually they die, and then the bacteria comes in, breaks it down. Bacteria uses all the oxygen in the system. No oxygen in the system means that the system dies. We also have what we call indicator species. So this is our biological indicators. So we have species that are more tolerant, and we have species that are more sensitive. So if we find a water sample with lots of tolerant species, that typically indicates that we have a lot of pollutants. If we find some with more sensitive species, it typically indicates that our system is nice and healthy. Pollutant tolerant means that they can withstand pollution, and pollution sensitive means that they cannot. Amphibians are one of our biggest indicator species because of their diffusion on their skin. So most of the time they are very sensitive to pollutants, and if we have lots of amphibians, lots of frogs, salamanders, that stuff, slimy stuff, that means our system's pretty healthy. And lastly, our color and turbidity. If we have any haziness, and remember we talked about turbidity, if we have a high turbidity level, we're generally going to categorize that water as being not healthy. So hazier, the murkier, the more suspended sediments, that's bad for our water. That's not good. That means that we might not have a very healthy water sample. So when we think about pollution, let's talk about how we deal with it, or how nature deals with it. Basically, the way nature deals with it is dilution. So once a pollutant gets into the system, there's really not much we can do about getting out, unless it's like a big piece of plastic, then we simply just pull the plastic out. But as far as like our chemical pollutants, really what happens is it dilutes. It gets, it becomes less because we have more water. So think about, would you drink a cup of water with 1 tablespoon of salt in it? Most of us wouldn't, because that's really, really salty water. But we could dilute it by instead doing a gallon of water with 1 tablespoon of salt in it. And that might not be so bad. So we're diluting it there. It's still the same amount of stuff. We still have 1 tablespoon of salt, but we're putting more water in it. And that's pretty much what we do, or what we hope for, with our water pollutants. We can also, some of them will biodegrade, which means that they are going to be broken up by bacteria, but it takes time. And natural bacteria can help degrade pollution naturally, so that's good, but it takes time. And dilution also takes time. So really the solution for pollution is to not pollute to begin with. And then lastly, we are going to go through the oxygen sag curve. So on the y-axis, we have distance downstream of the waste discharge. And on the y-axis, we have amount of oxygen in the river. So if you're looking at that big, thick line right here, this is showing us that. So as we get further down the stream, we are having first less oxygen, and then eventually it's going to increase our oxygen levels, which is good. So these are kind of the stages of pollution. So the very first thing we do is we have a pollutant that was thrown in. After we have a pollutant that was thrown in. So say it's like, say we have a bunch of nitrogen in the system. So the first thing that's going to happen is it's going to start to decompose. It's going to start to spread around into our water system. And then we call that the decomp zone. And then as it starts to spread around into our system, we reach what we call the septic zone, which is where only pollution-tolerant species can survive. So if you sampled a portion of water and you found a lot of tolerant species, then you could assume that it's in the septic zone. Eventually, we're going to reach the recovery zone, which is where pollution-sensitive organisms may survive. We're getting better here. The pollutant is starting to dilute. It's starting to become less of a problem. And then lastly, we have the clean zone, which is where we might find a lot of pollution-sensitive organisms surviving, and they'll be generally away from the dumping site. So if you're sampling or looking at, say we took, this is a river. So if we took samples here, here, and here, we would be able to identify possibly where the pollutant is coming from. So if I took a sample from right here, I could assume that the pollutant is upstream somewhere, because we are seeing just a few of those pollution sensitive organisms. We'll talk more about this another day though. But enjoy, have a great day.